Hi there, guys. So what we're going to do today is we're going to try to quickly touch base on the key information that you should have gotten from your reading on Monday so that I'm sure that you haven't missed anything of importance and that we're ready to move on into the next part of this. So the first thing we need to do is we need to identify some of the properties of acids.
Oh, bum.
I have no idea what that was. So, acids have a sour taste. Think citric acid, right? This is the acid that exists in all of our citrus fruit, oranges, lemons, limes. If they're not ripe enough, they're a very sour taste. However, for those of you that are asking this does not mean that we test for acids in the lab by tasting them. You never put anything in your mouth in lab. All right, moving on. Acids will also react with litmus paper. Litmus paper has an indicator in it which allows it to change color based on whether it's in the presence of an acid or a base. Acids always turn litmus paper red. It's more of a kind of a pinky in the reality of it, but anything to the red end is going to be acids. Acids always react with metals to produce hydrogen gas. Example, magnesium is a metal. It reacts with hydrochloric acid. This is a single replacement reaction. So that, remember, that's that high school relationship one, right? Where magnesium comes in, bumps hydrogen out, forms the gas. You see bubbles. That's a sign of a chemical reaction. That would be your... Acids are electrolytes. They dissolve in water and they can conduct electricity when they're in that state because of their ions. Now let's look at base properties.
Wouldn't be prudent.
Bases always have a bitter taste. So one of the most common bases are soaps. If you have ever accidentally gotten shampoo or body wash in your mouth, or I don't know if it was a joke or some people ever use this as a punishment, but sometimes in the olden days, parents would threaten to wash their child's mouth out, meaning, you might have tasted some soap. It's bitter. That's what bitter is. That's the sign of a base. Again, never test for a base in a lab by putting it in your mouth. Bases are slippery. Think of soap. It's slippery. When you touch it, if it gets wet, it's slippery, slimy. That's a base. Bases react with litmus paper. They actually turn it blue. So I think, now even though acids and bases both can burn your skin, really hurt your skin, we often think of acids as burning. And so I think acid, burn, fire, red. Acids turn litmus paper red. Bases start with a B, blue starts with a B, bases turn litmus paper blue. So that's how I remember those two and kind of keep it straight, if it helps. Acids and bases always react to give you a neutralization reaction. This is a double replacement reaction. It's when an acid and a base come together. We've talked about this. They always produce water and a salt. That is always the products of a neutralization reaction. So if you see any acid reacts with any base, it gets a salt. Now remember, how do we identify this? Remember, we have a little jingle for acids. Every acid begins with H, right? If you've got HCl, H2SO4, those are acids. You should recognize them right away. Bases, on the other hand, very often, but not always, have hydroxides with them. So those are kind of key, just off the cuff, what you should be able to recognize. We'll talk a little bit further later. So this is what a neutralization reaction looks like. Notice, here is your salt, here is your water. The hydrogen from the acid and the OH from the base is what gives you your water. Pull that out first, and you'll easily be able to see the salt with what's left behind. What's left behind is the metal from the base and the non-metal from the acid. That makes your salt. Remember, a salt is any ionic substance. Here are just some names of common acids and bases. And if you'll notice, a lot of these are things that you see around you all the time. Vinegar has acetic acid. Vegetables with their vitamin C is ascorbic acid. Soft drinks have carbonic acid in them. This is why they're so bad for your teeth and your bones and health and all of that. Citrus fruit has citrus acid. The reason bee venom hurts when you get stung is because of the formic acid. On and on. Ammonia is now a base. That's our first base that we're talking about here. And ammonia is really ammonium hydroxide. Calcium hydroxide. Milk of magnesia is something that your mom might have given you if you had an upset stomach, because the upset stomach is from your stomach producing too much stomach acid, which is hydrochloric acid. And so the milk of magnesia, which is really magnesium hydroxide, neutralizes that and calms it down. Okay, let's talk about the definitions. Arrhenius's definition, this is pronounced Arrhenius, is that an acid gives a hydrogen ion. This is also known as a proton. The only thing that exists in a hydrogen ion is its proton. And so hydrogen ion and proton are used interchangeably when we talk about it in science. So acids donate hydrogen. It's obvious that they can donate the hydrogen because every acid begins with that H, right? Bases, on the other hand, donate a hydroxide group, right? So sodium hydroxide is a base. Calcium hydroxide is a base. They have hydroxide ions to donate. So that's Arrhenius's definition. However, not every substance with H is an acid. Think methane. And not everything with OH is a base. This is methanol. It's an alcohol. It's not a base. So Bronsted-Lowry came along and they kind of fine-tuned their definition a little bit more. They kept the acid one the same. An acid is anything that donates a proton, right? So that's identical to Arrhenius's. However, for a base, theirs is anything that accepts a proton. So anything that can take that hydrogen ion floating around in solution and bring it into a molecule, that is a base. So therefore, there are now these conjugate pairs. Each Bronsted-Lowry can lose an acid, proton. Every Bronsted-Lowry base can accept the proton, right? Likewise, it could reverse, right? That base who now has a proton attached could all of a sudden donate that proton back, and the substance that lost the proton now has a way to accept it back. And so that's where you'll get these conjugate pairings come in. So let's see. This is key in identifying which ones are conjugate acid-base pairs. They differ by one hydrogen ion, one single proton. Okay. So where Arrhenius differs from Bronsted-Lowry is simply its base definition. Its acid definition is the same. So what is the Bronsted-Lowry base in this reaction? Notice there's no hydroxides here. So you can't use that Arrhenius's definition. Remember, Bronsted-Lowry is something that can accept a proton. So therefore, HSO4 negative, that ion, is acting as your base. It's accepting the proton. The proton is coming from right here on the hydrochloric acid. Notice that that then becomes a chloride ion. Notice that if the conditions are right, this sulfuric acid could donate this hydrogen right back, or to the, let me try this again, could donate this hydrogen ion right back to the chloride ion, and this reaction would reverse, and you would get hydrochloric acid plus the HSO4. So these these acid-base conjugate pairs are reversible reactions. Okay, Lewis's definition. Remember, Lewis structures that we did first semester were the electron dot diagrams. Lewis focused on electrons, where Arrhenius and Bronsted-Lowry focused on protons. Same thing, gonna get us to the same concept. It's just focusing on what's happening to part of the atom a little different. So Lewis's definition is, instead of an acid donating a proton, an acid accepts a pair of electrons. And instead of a base accepting a proton, a base donates the electrons. Just a different part of the atom to look at. Most chemists will focus on the Bronsted-Lowry definition of acids and bases, but I want you aware that this one exists as well. So, which is true of acids? I hope you said they turn litmus paper red. We don't have to, there we go. Have a great few minutes. I'll see you in the next video.